How many people here actually have to benchmark things? Raise your hand. You actually, people scream at you, things are too slow, you got to figure, okay, so what I'm going to be talking about are a couple of things you can do just to stay sane getting them done. Now, the first thing is there are two kinds of benchmarks. One has to do with timing, which are usually in the lies and damn lies department. Ours is two times faster. We've all seen those. You can always hack a benchmark to be as stupid as you want it to be. What I'm going to try and do here is show you how to avoid doing some of that. The other kind of benchmarks we all get into are functionality. Does something actually accomplish a thing? And I'm not going to talk about that today. Tomorrow I'll get into some of that with testing. But today I'm just really going to talk about time. The interesting thing about it is that performance and functionality, you get different things out of them. They have different needs, but a lot of their requirements is simple. You have to break things into atomic tests. You have to isolate what you're doing. So you can use what I'm talking about here for some functionality. The first thing to remember about a benchmark is none of these run in isolation. Anything you do with code runs on a computer. If you're running in a virtual machine, if you're running on a heavily loaded machine, if nobody's watching the test and you didn't realize that a cat sat on the keyboard, in there, you can get all kinds of problems with these. So make sure your environment is stable. That's the first thing to do. The simplest one, people here use time. Okay, that may be all you need. If you type time, whatever your thing is, and hit return, and it takes 1/10 of a second, and you say, gee, why do you think it's slow? You may be done. A lot of times, people don't pay attention. They think everything should be faster, and they just complain. Who knows? But time can be useful for a lot of things, a lot more than people use it for. The most important thing with time is run it at different times of the day, run something multiple times and get an average. If you run something once, you've got no idea how long it takes to go. We've all heard of Perl is too slow kind of things. There's one talk I have on lies, damn lies, and benchmarks that compares Perl and doing something with shell. You find, for example, people type ls and they'll type Perl with a glob and Perl takes longer. Well, yeah, because the ls is a special purpose. If you want to find things, by the time you're done piping 10 stages of something, it does take longer than Perl. So again, compare maybe what you're doing by running something with Perl, running it through the shell, type something shebang and see if you get a difference in time in the startup. Maybe your environment just takes a long time to load things into core. Get a baseline. This is a nice baseline. If Bash and Perl take the same time to start up, then at least you know that's not your immediate problem. What does that baseline tell us? That, 5 bazillionths of a second? Opterons are fast? I don't know. Basically, if those were significantly different, figure it out. For example, a lot of systems back in the day booted off of NFS-mounted platforms. You might find that bin bash was on a local drive and Perl was mounted through NFS over a wide area network over a 2400 baud modem with point-to-point. Perl isn't going to run as fast. Make sure that you've got something consistent as a baseline. A couple things you can do to control overhead I'll talk about up front. TempFS is a great thing. If you're going to write temporary data, if you're going to start up, if you're going to read files, stick the whole thing on TempFS and save yourself from things like disk overhead, SANs, heavily used networks, heavily used disk drives. Does anyone here really want to be competing with a data lake when you're trying to read your files? Probably not. Obviously, keeping the system load to a minimum. If you're using a virtual machine, that may be hard to do, but at least look at it. You may be able, if you're doing benchmarks, to have somebody up the priority on your virtual machine. You may be able to find either a bare metal or a real-time virtual machine to run the test on. If you can, do that. I'll talk a little bit more about it later, but TaskSet can be a big help for this also by associating what you're doing with one core, and that can improve your caching. It can save you on scheduling also. And a lot of the times are, how long does something take? And it depends. You may be timing something that does a lot of disk I/O. At that point, what you're really timing is how effective is the disk I/O in my computer? How effective is the driver? Am I using virtual drivers? A lot of people don't realize if you have a virtual machine and you install a kernel that's not virtual machine aware, you're using fake drivers for everything. Well, make sure that the kernel is designed to run in the environment it's running in, or you don't know what you're timing. You may be timing bad drivers, not your own code. And at a certain point, it make it hard to tell that. So, time for hardware, time for software, time for I/O, try and separate them. Do things that manipulate each of those, and you can compare the times for them. Realistic tests are hard to write because you have to isolate each of the things you're doing. So one thing is use benchmark module. People use that? Couple? Okay. This will do most of what you need it to. It will do it better than time. Use the high-res wall clock option. Just about everyone has access to the high-resolution wall clock, and timing things to the nearest second may not help you very much unless you're timing something that takes overnight. I've seen a lot of people, they have all these great benchmarks, they forgot to use high-res wall clock, and everything got rounded up to the nearest second. Test atomic units of code. That's another thing. If you think about it, the way you write tests is a lot of the same way you write benchmarks. You want to see how long does one thing take, another thing take. If you have code that might run in variable environments, test your exception handling. You might find everything runs just fine until something fails, and then it takes 75 seconds to discover that a DNS for a help file isn't available. Even end-to-end testing, if you've got to finish an end-to-end test, great, but test the pieces of it along the way to try and identify the bottlenecks. If you're running a virtual machine, people here understand time slicing. What you'll find is if you time things inside of Perl, you're not going to know about stolen time. You're not going to know about the time that your virtual machine didn't have access to the CPU. The time in the OS level probably does have access to that because the kernel does a better job of keeping track of that. So what you may find is that your wall clock time versus the system time may be at wide variance depending on how loaded the server is. If you do a time this and I do 1,000,000 copies of just an empty subroutine, I should be able to watch that run, or maybe 10 million, 100 million, but I should be able to watch it run at 100% of the CPU on one core uninterrupted. If I do something like this and I'm running at 50% of the CPU, don't waste your time. Find out why you're not chewing up a core right there. You might have a heavily loaded system. It might be that your job was niced. Whatever it is, find out, because until you can run something unfettered, you're not benchmarking it. So for example, I ran this thing just now on this notebook, and running 1,000,000 iterations wasn't even, I got a negative execution time. So even with high-res wall clock, I couldn't tell. That's a good sign that nothing's interfering with me. If I run 1,000,000 of those things and it takes 15 seconds, we got a problem. Again, solve that. I know so many places where people have said, oh, we knew the system wasn't running right, but we ran the benchmark anyway. We just don't waste your time. Come up with benchmarks that progress. Test something small, test something larger. If one of these benchmarks gives you something wacky, stop, fix it, find out what's wrong until you have a working baseline. Another thing you can do, both of these are easy to put into just a Perl -E line. Open dev null 1,000,000 times. If you can't do that 1,000,000 times quickly, find out why. Again, that's a classic sign of that is with Linux, if you're running something in Zen or VMware, and the person who installed the kernel didn't know that they have to install a hypervisor-aware kernel, you're using fake drivers, which means every time you poke what you think is a disk drive, you're going into software that emulates the disk drive. So you're really not testing your code, you're testing how slow the fake drivers are. If you run something in QEMU, it is slower than frozen molasses because of all the emulation at the CPU level and the device driver levels. Don't benchmark things unless you're really running it day-to-day in QEMU. At that point, that may be the appropriate benchmark, but at least establish a baseline that says to people, look, This is how long it takes the CPU to run. Don't blame my code. Without these baselines, you're toast, because you've got no way to prove what's going on. When you're running a benchmark, nice a copy of top. Top will tell you a few things. It'll tell you how many jobs are in the run queue. If you've got an 8 CPU machine and you got 45 jobs in the run queue, you got a problem, because you're not going to get enough scheduled time. Notice if your process is jumping between cores. If you go into top, you can see which core you were running on last. It's one of the options. You can put that where you can see it. If that number keeps changing, then you're really testing whether or not your L1 and L2 cache association is effective. You're not testing whether your code runs well. If you fork or if you thread, notice how many threads you've got. If something accidentally creates 800 threads on an 8-core system, you can't benchmark it at that point. Find out why you're creating 800 processes. If you look in top, you'll notice one column for I/O weight. On a well-regulated machine, that should always be 0. In a modern system with the amount of memory that these things have, you should never really see I/O weight unless you're in the middle of the backups or someone is running the query from hell on a database server. But in both of those cases, you don't want to be testing anything because the kernel itself is blocked. It's in kernel land. It's not out in user land where it can test your code. You want to run, even if you're running something that does I/O, you don't want to see a very high I/O weight, because all you're proving is that your code blocks very effectively. And TempFS helps on that. If you're doing a lot of I/O, you're testing ETL code. If you're benchmarking a backup utility, then do it on TempFS with test data, and that at least takes a lot of that I/O out of it. Compare the times you get with a baseline on TempFS to a baseline on a real disk drive, iSCSI, whatever you're using, and then you can say, well, don't blame my code, get me a faster network connection from my iSCSI. I know a place, they were complaining, their backups took all night, they were really, really mad at this database vendor for selling the slow equipment, and we found out they were using 10 meg Ethernet for iSCSI. Guess what? Didn't work very well. Latency was eating them. Well, find that kind of thing out before you run an end-to-end benchmark, because once you're up in your code and you've tested it, you can't test that lower level stuff. You really can't see what's going on. A couple of red flags to look for. High I/O wait times during your benchmark. Even if you're benchmarking something that does I/O, if you've got really high I/O, find out why and solve that, because you'll never get any decent performance if it's high. If the runnable jobs, again, is a lot higher than the number of cores you either have available or are on the machine, even if you've got a virtual machine that has 4 cores assigned to it, you don't know that there are actually 4 cores available when that virtual machine is running. So if you have the tasks approaching the number of cores, you've got problems, because you're going to be, the kernel itself can be limited on the number of cores it has access to, and your kernel may be sliced out of the CPU. Is this making sense the way I'm saying it to people? I'm getting some nods and some nod. The problem is that with a virtual machine, I can tell VMware or Xen or one of these things, I want to give 8 cores to this virtual machine. That isn't a promise, it's an upper limit. If there are 14 virtual machines running, and they're all in contention, you might only have 1 core right now. If there are 3 jobs running in your virtual machine and there's 1 core available, you're getting time sliced. You can run top. The top is going to show you X number of available CPUs, but a bunch of them are fake. You can't access them because some other virtual machine you can't see is using them up. So again, watch for these red flags. If you see a change in the amount of swap used, you've got a problem. You don't want to be swapping while you're running, and I'll show you a way to avoid that. Task set on Linux. I can task set myself to a single core. That will keep my L1 and L2 cache association high. It'll keep me running a lot faster. Again, it saves me from testing whether the vendor implemented their caching mechanism effectively. I'm testing my code. If you're going to be forking, do a test. You can do a range of CPUs. Try to pick one that are on the same core. Don't dance between CPUs, especially if you're on an AMD system where you're using non-volatile, the NUMA, because you're going to have to copy things between memory banks just to get to them. You're going to have to talk to other things to get to the memory bank you started from. Isolate yourself to at least a single CPU and hopefully one core. This is a cute trick. If you're going to run something that uses a non-trivial amount of memory, don't be in contention with other processes. The way to do that, create an array that is so big you get swapped, and then exit. Force everything that isn't running out of core. Then run your test, and you'll have as much memory as there is for as long as it takes them to get mad and come back into memory. A lot of people may be unhappy with you for 30 seconds, but at least you'll get a decent benchmark. This is the various versions of this memory hog. You keep pushing stuff on until you collapse, you do whatever. But to have something that swallows all of physical memory and then croaks. Benchmark has a baseline built into it that it uses. Don't trust its. Use your own. Get your own benchmark and see it, because you want to be able to see how it varies over time. Again, keep these benchmarks running. If you've got decent unit tests, run a time on each of your tests. That can give you an idea whether one piece of your code takes bloody well forever to start up. Just do a time on, if you notice when you run prove, you'll get timings. Use the timings from prove. Put benchmark into some of your .t files. But make sure that you know what each individual piece looks like. Again, that it gives you some idea what's going on. You can do time stir and time diff with the benchmark module. It's a good way to find out how long things take progressively. Time high res, the object exercise. Has anyone ever used that? It's a thing I've written that it allows you to use metadata to drive your tests. One of the options built into it is benchmark. If you use that, it will store a high-res time before and after whatever you ask it to gets run. The neat thing about it is you can design a long progressive test. You can create something in the database, create something else in the database, do everything in stages, and get the timings for each stage. That helps you tell, for example, if you've got one grossly unbalanced index in a database, and people are screaming that they hit return and it takes lunch to get something on the screen. You can start running individual queries and see how bloody long they take. You can isolate the problem down to a specific query or a specific chunk of your code. Adding benchmark to your shebang code and time will help you with end-to-end tests. I can take my shebang, I can put a benchmark at the top, a benchmark at the bottom, and just dump out the time when I'm finished. The problem with that, of course, is then you end up seeing it every time you run something, but that may be what you need. Also, take time to account for people. If you're testing a web backend, the time it takes somebody to type like this is going to be a lot slower. So you may have to do something like this. In the backend, put the times that you get and receive things, log the time that you do for each thing. Not for how long you ran to do a full end-to-end test, but how long did it take you to assemble the replies? The good thing about this is it subtracts out all the network latency and all the human latency in clicking the OK button. Dump these out at the end, put them in a file, dump them out as YAML, do it however you like. But this will allow you to track how long you're taking, subtracting out what happens after you get rid of the packets. So the summary is benchmarks do not have to be damn wise. You can write benchmarks that actually track what you're doing. Most of the problems with them that I've seen are people not controlling their environment, not establishing a valid baseline for what they're doing. Run incremental tests that go further and further into the code to isolate the problems. Use the high-res wall clock. You'll almost always, any modern system is going to have access to a high-res clock. And if you watch the system, verify your isolation. Procinfo NG on Linux will go a long way. You can look for high interrupt counts. You can look for lots of synchronous swapping while you're running. All of those things indicate the kernel is getting overloaded, and we're not benchmarking your code, we're benchmarking how well the kernel responds to the load being placed on it. Use task set, that will save all. Actually, if you're doing anything that depends on time, use task set anyway, just because it'll run faster. And then tempfs, you can see mount for some of the options with that. You can mount a tempfs, copy your data into it, and run out of there. And that will save you, again, from testing whether or not the kernel vendor implemented their drivers properly. It'll save you from testing whether your iSCSI is set to use the network effectively. And those things really will help a lot. Any questions? Everyone with a heartbeat, raise your hand. Okay, so people are at least partly awake. That's the problem with going after lunch. The people in the morning, it's like you've had enough coffee that you're paying attention. Did this make sense to people? Did this seem helpful? I'm getting some nods. Okay. I was asked to make really, really, really certain I finished on time, so I tried to go quickly. Anyone have any questions or any horror stories from your own benchmarks? Well, when people here are running, do most people here run with virtual machines, or you actually have bare metal to do your benchmarks on? Both. How many times have you had to benchmark something where you were running on a virtual machine? People have to do that? So you're benchmarking stuff that might run on Amazon, or you're benchmarking on something that runs in the basement, maybe with VMware. Do you have any access at all to the control information from the actual hypervisor? Things that would tell you, for example, whether your virtual machine is high priority or how much time was stolen from it?
There was something that gave you stolen time, but I don't know if I have it from access to it.
Yeah, if you have access to that, that can go a long way. I've had people screaming mad at me that the code I have ran too slowly, and we found out that I was getting like 15% of the available CPU. Well, don't blame me. But that's a lot of it, is make sure that you know what your environment looks like, because otherwise you have no idea what you're really testing, what you're trying to benchmark, whether it's your code or what lives under it. Like I said, things like the disk hog, like task set, using high-res wall clock can go a long way towards getting the effective benchmarks done. Yeah?
Just to let you know, I mentioned this in a previous session. We now use cache drive completely for doing benchmarking. And we have things so that isolates everything. Just
Okay.
instructions. And then we have somebody who's assembled a benchmarking but a data set of current benchmarks. So,
Okay. That gives you a decent baseline to start from.
And we see it will fail test if we exceed that by too much, by changes.
That's a good one. That's a good way to start. Would you be willing to get me, is there a link that describes the caching and the Valgrind? Because I can put that in here before I stick it on the wiki so people can see how to find it.
I'll talk to you afterwards.
Yeah, afterwards, if I can find that, that'd be neat.